good evening everyone. We are here to learn class 10 mathematics, and the topic that we are going to discuss today is real numbers. So let us begin with real numbers. So I hope we have learned about this topic in class 9th as well, and therein we learned about some numbers. For example, we learned what are real numbers, what are rational numbers, what are irrational numbers. So let us have a very quick recap of how we categorize numbers. So if we say that, if you are talking about real numbers, so real numbers can be further divided into two categories: rational and the second one is irrational. And we learned quite a few things about rational and irrational numbers. So if you recall, rational numbers are numbers that can be written in the form of P upon Q, and wherein Q cannot be equal to 0. So the denominator has to be a non-zero value, or Q has to be a non-zero value. Okay, and then we also learned about irrational numbers. So these are the numbers that cannot be written in the form of P upon Q. Okay, and then we know about integers, whole numbers, natural numbers. So integers are the numbers wherein we have positive numbers, negative numbers and 0. Natural number starts with 1, whereas whole numbers start with 0. Okay, so these were all about the numbers that we had learnt in class 9th, real numbers. Now here today the first topic that we are going to discuss is about Euclid's division lemma. So first of all we have to understand what is lemma, and then we can discuss about this lemma, because this is the first topic that we are going to learn today. So let's talk about what lemma is. So if you go through your NCERT books, you can see this. So it says that lemma is a proven statement used for proving another statement. So if you want to prove any statement, you can use a lemma, which means we can use a statement which has been already proved. Now let's come back to the division lemma, Euclid's division lemma. Okay, so the Euclid division lemma says that A equals BQ plus R, wherein A and B are given positive integers. Okay, now to simplify this, we know we have already learnt about division lemma in previous classes. So let me just simplify this for you. So we have all learned this, which says that the dividend equals the dividend equals divisor and times quotient add remainder. Okay, now if you look at this, the division lemma, it says A equals BQ plus R, and where the value of R is equal to 0 or greater than 0, but it has to be less than B. That means it has to be less than the divisor. So R can never be greater than the divisor, and we can write a division statement to just quickly recall what is a dividend, what is a divisor, and what is a question. So for example, if I want to divide, say, 47 by 3, so we know that we can divide this by 15, and the remainder would be 2. So this 15 is the quotient. I am denoting it with Q. This is the divisor. This is remainder, and this is dividend. And this says that if I want to write this division in form of the lemma, the Euclid's division lemma, I would write this as so we know the dividend is 47, and the divisor is 3, and we are multiplying 3 by the quotient, which is 15, and when you add 2 you'll get 47. So now let us do one thing. Let's compare this with the lemma. So if you see, A is 47, so let us quickly write down the values of A, B, Q and R. So here the value of A would be 47, and B is 3, the divisor. Q is quotient, which is 15, and then we have R, which is equal to 2. So I think we have all done this in 7th, 8th, 6th classes, wherein we know that when you divide, you'll get the quotient times divisor, add the remainder, would give you the same number. So this is what the lemma says. Now it says that the result of this we know already. We have first learned this in we have learned these in our primary classes, the secondary classes, and now we are going to learn about this lemma using an example. Now let's see how does this lemma helps us. So Euclid's division lemma or algorithm is a technique to compute the highest common factor, HCF, of two given positive integers. So we can use this algorithm or this lemma to find out the HCF of two integers. Now if we recall, what is HCF? HCF is the highest common factor. For example, let's take a let us take very simple numbers. So if I ask you to find out the LCM of 18 and 27, so how do you find out the LCM? So for that we have to look for the numbers that is the that is the biggest number that can divide both of them. So if I start categorizing all the numbers that divides 18 and 27, I can make a list. So we know that 18 and 27 are divisible by 3, and then if you check 6, 18 is divisible by 6, but 27 is not, so we cannot say 6. Then the next number that comes to my mind is 9, and if you check, 9 divides 18 as well as 27, so that would be 9. And now you cannot have any bigger number that can divide both 18 and 27, so the HCF of 18 and 27 would be 9. Now you must be wondering that we can easily find out the HCF using prime factorizations, or like we have been doing this. Then what is the need of learning this lemma? Well, we all have been doing this, but we just didn't know that we were using this lemma to find out the HCF. And you can also use this algorithm works for bigger numbers as well. For example, if you want to find out the HCF of the integers, say 455 and 42, you can use this algorithm to find out the HCF of these numbers. Okay, let us do one thing. Let us first understand the example, and then we can sum up the steps that we need to find out the HCF of these two numbers. Okay, so we are starting with the Euclid's lemma. If you check, this is of the form A equals BQ plus R. Okay, now I think student might have this confusion that when you have two numbers, like here you have 455 and 42, so how do you decide which number is going to be A and which number is going to be B? It's really simple. Like, we have to let's go to the steps first. So the step 1 says that apply Euclid's division lemma to C and D. Okay, what we can do is, because to avoid confusion, I'm just going to make it A and B all over. B, and then Q and R remains the same. So this is basically A equals BQ plus R. So if you're applying division lemma to numbers A and B, they can be anything. We are talking in general here. They can be anything. For example, they can be 18 and 27. They can be any two numbers. Now, how would you know that which you should assign A and which should be B? So this is the criteria. So whatever number you are choosing for A should be bigger than the other one. So the bigger number goes for A and the smaller one is the B. Okay, so and the smaller one becomes the divisor. Alright, so what we do is we have identified A and B, so the bigger number is the dividend and the smaller one is the divisor, and then we can find out what divides, the maximum that we can divide that to find the Q, and then we can find the R. So now let's come back and apply that here. So here we want to find out the HCF of 455 and 42, and we can do that by applying the lemma first. So the lemma says, I'm going to write the lemma again so that it's easier for you people to relate. So this says A equals BQ plus R. Okay, so 455 is A, 42 is B, Q is 10 and R is 35. So what we have done here is we have written for 455 as 42 times 10. So if you do 42 times 10, you'll get 420, and the remaining number is 35, so we added that. Okay, so this is the lemma that we applied. Now what is the difference between algorithm and lemma? So lemma is the first step that we did. Algorithm is a series of steps. So in the first step you apply the lemma, but if you are solving the question in 4 steps or 5 steps, all of those steps will make an algorithm. So this is a well-defined step. Any well-defined step for anything is algorithm in general. Okay, so here the step 1 was to apply division lemma, which we did. Now you already can see that R is 35, Q is 10, A is 455, B is 42. Now let's move to the next step. So the step 2 says if R equals 0, then D is the HCF of C and D. Okay, again because we are talking in terms of A and B. So if R equals 0, B would be the HCF. So if the remainder is 0, then the divisor is the HCF, but the condition is that R has to be 0. So until and unless we are getting R as 0, we have not reached the HCF yet. Okay. But so because the previous step where we applied the lemma, here we applied the lemma, but the remainder is 35, it's not 0, so this is not applicable yet. Now the next condition says if R not equal to 0, apply the division lemma to D and R. Okay, so basically we have to apply the division lemma to B and R. Okay, so for the next step, I'm going to write down the value of B and R. So B is equal to 42 and R is 35. Now what happens is we are going to apply the lemma to these two numbers, and again if you compare both the numbers 42 and 35, you'll see that 42 is greater than 35, so you'll write 42 equals 35 times 1 adds 7. So again, if you look at the remainder for the second step, it is still not equal to 0. So that means we have to continue the steps until and unless we reach 0. Now then for the next step, the value of, let's find out the value of B. So for the next step, the value of B is 35 and R equals 7. Now let us write the third one ourselves. So how are we going to write down the third one, for which you are going to apply the lemma? So let's say, so I'm going to write that here. So that would be 35 equal, now what would you time 35, now how many times 7 is 35? We all know that 7 times 5 is 35 and add 0. Now at this point we got 0 as the remainder. So for this step, after this step, we can say that the remainder equals 0. That means we have got our HCF, which is this. Okay, let's check if we have gotten the correct one. So here we go. Now consider the divisor. We did this already in the previous slide, and it says that now the remainder has become 0, so we cannot proceed further, we cannot further apply the lemma. Okay, so now we can say that HCF of 455 and 42 is the divisor at this stage, that is 7. So the HCF of these two numbers is 7. So basically you'll get HCF at the last stage of the algorithm wherein the remainder is 0. So for the step where the remainder is 0, we get our HCF there. So it's very simple. You have to continuously apply the lemma, making sure that for the second step, when you have applied the first step, for the second step you are going to take B and R, and then you are going to put that in the lemma. And till when we have to continue? We have to continue till the remainder becomes 0. And this is the algorithm. This is Euclid's division algorithm, wherein we have defined 3 steps. So the first step is really what we have to do, in the beginning. So that is, if you are given 2 positive numbers, you'll have to decide which is A, which is B. Then you have to apply the division lemma to it. If your remainder after applying the first step is 0, you got your HCF in the second step. If not, you have to continue applying lemma until you get your remainder as 0. Okay, now let's do one thing. Let's try out some questions on the division lemma. Okay, so the first question is, we have to find out the HCF of 135 and 225 using the Euclid's division lemma. Okay, so I'm going to quickly write down the numbers. So the numbers are 135 and 225, I believe. Let me just check. Sorry, it's 200, yeah. So 135 and 225. Now what we are going to do is we are going to apply division lemma to find out the answer or the HCF for these numbers. So what is the first step? If you compare these two numbers, let us first write down the values of A and B, and then we can apply the lemma. So A would be 225 because we have to fulfill the condition that A is greater than B. So if you compare both the numbers, 225 is bigger, so that would be A, and then what would be B? B would be 135. Okay, and now let's continue applying the lemma. So we'll write 225 equals, so how many times 135 would you get 225? I think that would be 135 times 1 times 1. So if you times 135 by 1, you'll get 135, and that's how much short? That's 90 less than 225. Okay, so this is the first step. Now if you look at this step, you'll observe that R is not equal to 0, rather R here is 90, and the value of Q is 1, yeah. Okay, now for the next step, to apply the next step, so this is step 1. For the next step, we'll take B and R, and R is 90, B is 135. So now we are going to apply the lemma to the numbers B, which is 135, and R, which is 90. Okay, so how would you write down the next step? So I'm going to write down the next step here. So if I apply lemma to B and R, that would be 135 equal, now if you see, 90 times 2 is 180, so you can only do this 90 times 1, and rest everything would be the remainder, and if you subtract, you'll find that the remainder would be 45. Okay, now again, this was the second step that we did. After this step, we again got some values for B and R. This time the value of B is 90, and the value of R is 45. So again we are going to do step 3 by applying the lemma for the third time on the numbers 90 and 45. And now for this one, I'm going to write 90, which is equal to 45 times 2, and what would be the remainder? The remainder would be 0. So that means we have reached the last step and we have got our HCF. Now what is which number is the HCF? This, the B, the divisor. So that means we can say that the HCF of the numbers 225 and 135 is 45. Okay, now there's one way of writing it. You can also write HCF like this. So what you do is you write HCF. Okay, it's a bit hard to write like that, but yeah, I'm trying. So okay, let me do this. I'm going to use the text. So you can write HCF like this. So we have figured out the HCF for the numbers 225 and 135, and the HCF is 45. So this is how we can write down the HCF of the numbers. We denote it like this. So you know, it pretty much sums up that the HCF for the numbers that are in the brackets is 45. So sometimes in questions you might have written the HCF for numbers might be written like this. Okay, now let's come to the second topic that we're going to discuss today. So we learned about division lemma, we learned how to apply it, and we also learned that why we use the lemma. So we use the lemma to find out the HCF of two numbers. Okay, now let's see the next topic. Okay, now if you go by this chapter in NCERT, you'll find out there is an example too, which is really important, and now we are going to learn about this example. So the example 2 says that show every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Now you must be wondering that how is it related to what we have just learned. So this is another application of the lemma. For example, in the first application we used the division lemma to find out HCF of two numbers. Now we can also use the same lemma to find out, to prove certain certain facts. For example 2, we have to prove that every positive integer is of the form 2q, and every positive odd integer is of the form 2q plus 1. Before we actually go into this example, we have to see that we have to use a fact here that we have learnt about the division lemma. So the fact that you have to use here is this one. I'm going to double circle it, this. So you have to remember that the value of r has to be less than b, but it can be greater or equal to 0. That means r can never be any negative numbers, so either it's 0 or it's positive numbers, as we have seen in the example. So when you get the value of r as 0, you have gotten your HCF. Now this is something we are going to use in the questions here. So let us come back to the example. Okay, now whenever you are asked to prove something, you see it's 2q. So let's do one thing. Okay, let's go to a blank page. I'm going to rub this out. Okay, now let's see. I'm going to write the division lemma again, which is a equals b q plus r. Okay, in the example, in the given example, if you have books, you can refer to them. So I'm just because if I go back and then come back, it would take a lot of time. Okay, so it says that every positive integer is of the form 2q, and that every positive odd integer is the form 2q plus 1. Okay, so I'm going to write down what is already given to us in the question. So it says for even the form is 2q, and it says for odd the form is 2q plus 1. So this is what is given in the question. I can write. Okay. So you just